This lecture is about positive and negative predictive values. So now we've learned what sensitivity and specificity tell us about a test and some of the limitations. Let's now go back to our 2x2 table, and this time we're going to be focusing on the rows rather than the columns. Positive predictive value relates to the first row and is the proportion of individuals with a positive test who have the diagnosis, or A divided by A plus B. Negative predictive value comes from the bottom row and is the proportion of individuals with a negative test who don't have the condition, or D divided by C plus D. Using the same figures as before, we can calculate positive predictive value as 95% and negative predictive value as 99%. Let's apply this knowledge to our woman with a positive pregnancy test. All women in the top row have a positive test and 95% of them are pregnant. As she has a positive test, her chance of being pregnant must also be 95%. Similarly, if the test was negative, there would be a 99% chance she was not pregnant. At first glance, this seems to solve the problem we encountered with sensitivity and specificity, as PPV tells us the probability of pregnancy with a positive test, and NPV the probability of no pregnancy with a negative test, which is exactly the information our patient wants. Unfortunately, things are not quite so simple, and this is because predictive values vary with the prevalence of the condition within a population. Let's look at a diagnostic accuracy study performed on two populations with a different prevalence of pregnancy to illustrate this. In our initial study, 200 out of 450, or 44% of women were pregnant, and the 2x2 table looked like this. If we repeated the study in a population where the prevalence was half at 22%, the table would look like this. Sensitivity and specificity are unchanged, but the positive predictive value has reduced from 95% to 88%. Based on this second study, we might predict that a woman with a positive test was 88% rather than 95% likely to be pregnant. Clearly something is wrong here, as we're performing the same test on the same woman. The only thing that's changed is the prevalence of the condition during the diagnostic accuracy study. The reality is that predictive values vary with prevalence, and therefore cannot accurately predict the probability of the condition, unless the prevalence in the diagnostic accuracy study and in the women you use the test on is identical. This graph is based on a test with a sensitivity of 90% and a specificity of 99%. It shows how PPV and NPV vary between 0 and 100% depending on the prevalence of the condition. The obvious question, therefore, is how can we decide the probability of pregnancy or any diagnosis using data from a diagnostic accuracy study if sensitivity, specificity, and predictive values can only rarely give us the correct answer? The answer to this conundrum lies in Bayes' theorem, which is the subject of the next video.